our third presentation of the afternoon. I keep losing my schedule. That is Ayush Chopra. Ayush, you there? In there? Good.
Hi. Good
Awesome.
morning.
Take it away whenever you get a chance.
I just want to make sure you can see my screen.
Yep, we're good.
Perfect. Okay. Hi, I'm Ayush, and I'll be talking about our work on learning behavioral policies over networks of interacting agents. The main premise underlying our work is that how machine learning can support the transition to IGSS by enabling adaptive actions and faster interactions in agent-based models. So this research sort of stems from our collaboration between MIT and Adobe. So I'm Ayush, I'm a PhD student at MIT. My research is in machine learning and reinforcement learning. So I think this is a great segue from the previous talk, where we're sort of delving into the transition from agent-based modeling to a reinforcement learning perspective. And I'll be giving this talk with Jay Kumar, who is my collaborator from Adobe. He's a senior research scientist at Adobe, and he has a PhD in multi-agent reinforcement learning, which sort of provides a good contextual environment for thinking about agent-based models and learning in those setups. Okay, so this is not new news for anybody in this call today, but generally over the last year, we've been living in interesting times. And one thing that has come up sort of these times have reiterated the importance and the potential of agent-based models. So in today's time, sort of critical decisions for society and economy require navigating a series of what ifs. Like we've been thinking about questions like, what if we reopen schools in 100 days? What if we delay the second dose? What if there are vaccination parties? These are a wide variety of tools that are questions that need to be answered and which can have significant impact on our future. And experts need better tools to answer these what if questions to make faster and better informed decisions at population levels. Consider, for instance, a question. Now, these questions are challenges because decisions for populations may not be obvious by observing single individuals, which sort of lays down the premise for our research in agent-based modeling. Consider, for instance, this question during the COVID pandemic. Can faster, less specific tests be more effective than a slower, more specific test? When you ask a single individual, this may often be a trivial question. Everybody wants as efficient and as specific tests as possible. But using simulations and using agent-based modelings, we realized that under specific constraints, test turnaround time can often be more important than the test specificity, which sort of segued into our interest in agent-based models, which can enable us to simulate the action and interaction of multiple agents to assess and predict population level effects. Consequently, coming from a machine learning background, our perspective was, under this setup, how can machine learning enhance agent-based models? And we decided to break down the study into two components. We feel that machine learning can help us do faster simulations and do adaptive simulations. And we'll be talking about each of these two components in detail in this presentation. So for faster simulations, we propose a new framework for doing agent-based modeling. It's called the DeepABM Framework, which takes a more tensorized and network-centric approach to building agent-based simulations and can significantly accelerate and scale performance in agent-based models. The second part will be on doing adaptive agent-based simulations, where we bring out work in multi-agent reinforcement learning to present one possible technique which can be used to learn policies or adaptive rules for agent behavior. Okay, so first I'll be talking about the work in faster agent-based simulations through the DeepABM framework, and then Jay Kumar will talk about adaptive agent-based simulations. So the premise for the first part of DeepABM is that agent-based models provide us a framework to model heterogeneous populations, and they can study complex time-varying actions and interactions. However, generally the simulations are computationally expensive, prohibitive to implement, and often difficult to configure and parameterize. Hence, to really scale practical utility, it is important to make agent-based models scalable, efficient, and highly performant. To achieve this, we seek to bring said scale, efficiency, and performance to agent-based models by reimagining them in machine learning frameworks. Specifically, we bring together work in deep learning and multi-agent systems and introduce a tensor calculus-based implementation of agent-based models that specifically models local interactions through graph convolutional frameworks. The benefit we achieve is that we are able to scale agent-based simulations to large populations, more than 100,000 agents seamlessly, efficiently execute this 100,000 agent simulation in real time on a GPU by bringing in diverse data sources, as well as calibrate models efficiently using machine learning instead of doing random grid search. So to do this, we introduce a DeepABM framework. So the basic concept underlying the DeepABM framework is that most conventional agent-based frameworks take an agent-based perspective to the infrastructure. So there is an agent and agents are interacting with each other. In contrast, we take a more network-centric approach to the simulation. So at the center of our simulator lies the network, which we implement using existing geometric deep learning frameworks. One particular that we use is called PyTorch geometry. And specifically, then we are able to represent individual interactions between agents using a popular PyTorch geometric deep learning technique called message passing, which can simulate interactions between agents, which can sort of parallelize interactions between agents on smaller induced subgraphs and significantly accelerate computation at every time step in sort of multi-step simulations. So effectively, DeepABM, the framework that we build, can significantly accelerate and enhance forward simulations by scaling agent-based models to large populations in real time, enabling efficient GPU-based computation, and also enable us to calibrate agent-based models using gradient-based learning instead of doing conventional grid search techniques. So we validate the benefits of DeepABM by simulating COVID-19 spread and interventions. And we build an extension called DeepABM Covid. The DeepABM Covid has 3 key configurable features. So at the center of these networks lie interaction networks. We also need to model disease dynamics, and we provide support for a large variety of interventions. So the interaction networks are of 3 types, which are household networks, occupation networks, and then random networks, which characterize random interactions. So the premise is that at any given point of time, every agent in the simulation belongs to one network of each of these 3 kinds. So every agent belongs to one household, one occupation type, and then there is a global random network. For disease dynamics, we support multiple stages of infection, which represents the natural history of disease evolution, which happens at an individual level. Everything is age stratified, and we can also model support for diverse kinds of strains. And we built this framework to study effects of various interventions, including quarantine, exposure notification, testing, and vaccination, just to give a plug-and-play framework to conduct simulations of COVID-19. From a quantitative standpoint, to sort of ground the benefit of using DeepABM, with DeepABM, we are able to simulate 200 million interactions over 100,000 agents across 180 time steps, where one step or one tick indicates a day. And we're able to do this in 90 seconds as compared to an equivalent implementation that we did in MESA that took 5 hours. There are significant performance benefits of using the DeepABM framework. I'm happy to sort of go over these details, like in question sessions or share code after the talk. So specifically, we used this and collaborated with epidemiologists and public health experts to answer a bunch of questions. The first question we were trying to answer is, what if we delay the second dose of the COVID-19 vaccine, and specifically the Pfizer and Moderna vaccines? This project was a collaboration with clinicians at Harvard Public Health, Mayo, and Arizona State University, and it was recently published at the British Medical Journal. And we realized using these simulations that under specific parameter considerations, we could delay the second dose, which could significantly reduce deaths at a population level. We can also use this to study more social implications, which include questions like, what if people increase interactions after taking the first dose? While this question is probably moot now in the US, where vaccination levels are pretty high, in major parts of the country, especially Southeast Asia, where I come from, vaccination is still picking up at a slow pace. And as governments and institutions start to vaccinate more younger people, these questions can become increasingly important. So using DeepABM simulations, we could show that increased interactions after getting the first dose could lead to a 2x increase in deaths, even if vaccination continued. Subsequently, we believe that DeepABM can be used for several COVID modeling, several setups beyond COVID modeling in public health economics, since it can enable us to model complex and adaptive human behavior, what we'll be talking about in the second part of the presentation now, as well as estimating network effects, which is the propagation of individual decisions and local shocks, which sort of our representation using a graph neural network framework to model agent interaction helps. Next, I'll pass it on to Jaykumar to take over the presentation.
Thanks, Ayush. So this part of the work that Ayush currently presented has already been published. And what I will be talking about is the work that we are currently focusing on. And we have some preliminary observations, but at this point of time, what I'm going to present is more on our thought process and our modeling framework. Can you go to the next slide, Ayush? So I will begin by just setting the notation for reinforcement learning. So as a standard in reinforcement learning, there is an agent that acts in an environment. So the agent learns to act optimally by repeatedly interacting with the environment. Each interaction is characterized by 2 steps, where the agent receives the observation from the environment and a reward for its prior action. And the agent, noting this and the entire history, chooses to act in the environment given the current state. So the agent does this repeatedly to learn a policy, which is a mapping from all the information that the agent has to either a deterministic or a stochastic distribution over actions to take in the environment. The mathematical framework that typically people use to represent reinforcement learning is Markov decision process framework. And the solution concept is finding an optimal policy or optimality in this setting. Ayush, can you go to the next? So I'll spend slightly more amount of time on this slide, where we talk of extending reinforcement learning to multi-agent reinforcement learning and why MARL is not multi-single agent RL. So to contrast with the earlier framework, the mathematical framework for RL was a Markov decision process, where the inherent assumption was that the agent is acting in a stationary environment. Here, the agent is acting in the corresponding mathematical framework is that of a partially observable stochastic game, and the agent acts in a non-stationary environment. This can be seen in this particular manner, that for each agent, as for instance shown in the slide for agent 1, all the other agents also become part of the environment. So as far as agent 1 is concerned, there is a transition behavior and a reward function determined by the environment, which is also influenced by the policies of other agents, which are also adapting. So each agent faces a non-stationary environment, and hence it is not a straightforward optimization problem, even though each agent is selfish and is trying to maximize its own cumulative discounted or average return. Here, typically game theorists have used various refinements of Nash equilibria solution concepts. However, it is like not very easy to compute these analytically, except for very simple games. So in the literature in multi-agent reinforcement learning, we find that there is a lot of work that has been done on very specific subtypes of games, such as zero-sum games or games with 2 or 3 agents, where it is fairly easy to numerically compute and track the behavior of all agents, and also in some cases to justify that they converge to a Nash or a subgame perfect equilibrium. There is also literature which takes it to the other extreme, where you consider a system with almost infinite number of agents or a very large number of agents, where each agent's contribution to the entire population becomes negligible, and we call this as mean field systems. And there also we have some analytical and numerical or computational results for reinforcement learning. But ABMs present a very different challenge for RL, because they are neither in the category of extremely large population, like we cannot assume that the population is infinite and hence derive some statistical simplifications, nor is the population small enough to be handled in conventional way, which is what piqued our interest in MARL in ABMs. Ayush, can you go to the next slide? So in order to first test out like what we wish to present about ABMs, we were looking for what are good environments where reinforcement learning would make sense. We started with a COVID ABM environment, but in the COVID, the disease dynamics are well known and several aspects of the environment are studied independently, which then makes RL not quite interesting. Then we came across several environments from economics, which traditionally have been solved using equilibrium-based methods such as DSGE methods, or using agent-based methods where you have a few classes of agents, but multiple agents of each class, which interact with the environment in various configurations. So in order to do our study, we picked one such environment, which is by Kayani et al., where they consider 6 types of agents which interact in an environment. So we noticed that there is a certain gap between the MARL community and the ABM community. And with this environment, we thought we could understand and bridge this gap to some extent. So the first part was, as Ayush mentioned, like splitting the behavior, splitting the environment into 2 aspects. One is the transition and the rewards, which is governed by the environment independent of the agents. And the second is the policies of all the agents interacting in the environment. In this particular environment, we have 18 interaction events in every step. And typically in multi-agent RL or in games, we have that in every step, all agents either contribute, interact, or agents act in a sequential manner, which in each step only one agent acting. But we noticed that some of the ABM environments for economics have a very different kind of structure where each period is characterized by multiple interaction events. And in each event, there are multiple number of agents that act, often with differing informations. So this actually lends a different challenge to MARL, which I'll describe in the next slide. So this is a timing diagram for interaction for agents. And some of the concepts which we wish to bring out using this diagram is the fact that different agents act at different points in time. But at different points in time, they have different information. For instance, like in this particular case, we have divided the timeline into 18 events for every time. And after every 18th event, the sequence repeats. The capital firm and consumption firm, for instance, act at times 1, 2, and 18 as well. And their behavior could have evolved in when they are acting in these various events. The household, which actually only operates at the 18th time step in this particular timeline, can or cannot observe the capital firm and consumption firm's interactions in the first few events. And therefore, the response that the household has to the capital and consumption firms might differ based on what information it has access to. So hence, like we find that information structure is a crucial component, which will again bridge ABM with MARL-like concepts. So next, I would like to consider one particular case of one agent doing MARL and how the structures vary for the ABM perspective. So in this particular case, we have a framework where we divide the entire problem into finding 4 functions for generating emergent or resultant behavior. So the 4 functions or 4 classes of functions are policies, the transition functions for the environment, the observation functions, and the reward function. I'll try and go over all these in detail, and please feel free to ask any question if something isn't clear in this particular case. So I have just taken the case of household agents which interact with the environment. So at each event where the household is allowed to interact, it receives an observation, which is based on the transition and observation functions of the environment. And it receives a reward, which is a function of its prior action. And if it's the first action, it does not receive any reward. At every event, based on the current information, the household has to choose what action it has to take. So if the household is involved in, say, 10 events, it will have 10 policy functions. And each of these policy functions can be learned independent of each other. So similarly, it follows for all the other agents. And the difference from conventional MARL algorithms is that in conventional MARL algorithms, each agent has only one policy that it needs to learn. The other assumption that is normally made in ABMs is that all agents of a particular type use the same policy. So even though the actions might be different because the agents have different states, their policy function is still the same. We are currently exploring the possibility that different agents within the same type also have different policies and different learning algorithms. As was pointed in the earlier talk, like agents can exhibit type 1 and type 2 behavior. And typically we see that ABMs with fixed policies like are closer to type 1 kind of behavior, where even though the agents adapt their policies, the adaptation is like fixed in terms of heuristic rules. We also have a provision where agents can learn using deep multi-agent reinforcement learning, which can also use the entire history instead of just the current observation of the agent, and give it more of a type 2 or system 2 kind of characteristic. So these are the features by which we plan to link our DeepABM framework concepts from multi-agent reinforcement learning to quickly simulate emergent or resultant behavior using these 4 functions, which are the policies, transition, observation, and reward functions. So one of the advantages we have using the DeepABM framework is that RL or MARL often requires multiple forward passes through the environment in order for the agent to learn. So it's a huge difference if we can reduce something like a forward simulation timeline from 5 hours to say a couple of minutes. Then we can it becomes feasible for us to have multiple runs to do reinforcement learning. The other thing that we also wish to investigate is that so far we have spoken about agents having fixed objectives or fixed utilities, as was discussed yesterday as well, that the utility theory is not completely settled as to what objective the agent has to optimize. So here we are sort of saying that can we have a distribution of various objectives and then try and modulate that to see what distribution of objectives, what distribution of learning algorithms produces the requisite emergent behavior. And again, here our PyTorch ABM-based framework helps us because we track the computational graph throughout. We can effectively get gradients with respect to any trainable parameter. And subject to conditions of, subject to Lipschitz continuity approximations and some such technical conditions, we might be able to get at least some feasible inverse solutions. Specifically questions like if this is the targeted behavior, what should the agent policies or agent learning algorithms or agent utilities have been that led them to optimize and reach this particular behavior? And we could also possibly answer questions about what would have been the observation function that the environment chose in order to lead to this particular emergent behavior, or what is a transition function, like some production functions that we choose in economics, would a choice between deterministic or stochastic transition functions change emergent behavior? And if so, can we find out or ascribe like how exactly these parameters lead to the behavior that we want? So this was our idea about DeepABM, using DeepABM for forward simulations, and then ultimately using DeepABM for inverse behavior learning. Ayush, next slide. So so the objective of this presentation is that we wish to sort of reach out to people with the problem that we have solved. Our code is available for people to use. And then we also want to identify interesting problems and possibly prioritize our research areas so that we can tackle the more interesting parts first. Ayush, do you want to take over?
Yeah, I think we can take questions. Thank you.
Thank you.
Great, thank you, both of you. And of course, if there are any questions, we have a few minutes available before we break for, I guess, an early lunch here on the East Coast. But if anybody has any questions, let me know. So I think you mentioned this briefly, but I was kind of curious. You talked a little bit about how you were looking at the COVID-19 spread and policies that potentially alter COVID-19 spread. Was any of this information actually taken advantage of, or have you been in contact with any governmental organizations that might use that?
Yes. So actually, yeah. So we've been in contact through multiple avenues. So one of the avenues is, so my advisor at MIT runs something called the PathCheck Foundation, which is the largest nonprofit for building software for COVID at the moment. So he has been an advisor with several governmental institutions. We've deployed apps across multiple states in the US and countries across Europe.
Oh,
sorry.
You have a fire alarm going off.
I think so. Sorry. Jay Kumar can probably take.
I hope you're okay. If you need to run outside, please do so. Don't worry about the conference, right? But thank you. Rob, I see you have your hand up.
Yep. So you guys mentioned that it is conventional in reinforcement learning to have just one rule fires typically. One immediate ambiguity that enters when you have multiple rules per agent is, do you process the agents one at a time and fire all the rules at once? Or do you fire for example, rule 1 across all the agents and then fire rule 2 across all the agents? Or of course, there's combinatorially rich ways to handle that. And in fact, probably it should be an empirical question as to how people actually do that in their economic lives. So do you guys have any robustness ideas about how to treat such ambiguity?
So the entire MARL community, this question has not been settled.
I know that.
So people are asking these questions quite often. So essentially, most of the literature is on simultaneous move games. So where they think that all the agents act simultaneously. From a theoretical perspective, even the sequential move games can be considered as simultaneous move games, where all the other agents execute no-op actions whenever they are not permitted to act. But from a more practical perspective, that is one of the things that we wish to explore here, which is why I showed the timing diagram, because we believe that it is very crucial as to when the agent acts and what information the agent has when it acts will change the emergent behavior. Like we could fuse some of the 18 events together to say that the agents submit their policies at the same time, and the environment will schedule the actual implementation of the rule. That would change the behavior vis-a-vis the agent is allowed to observe the effect of event 1, and then it gives out what action it will take for event 2. The question that we do not know is how will it change emergent behavior? Will it change drastically or no? In some very small toy problems, it has been shown the difference between subgame perfect and Nash equilibria for such games. But we hope that we can observe such effects in a much larger ABM setting as well.
I think that just as a follow-up, there are several examples in finance where the hope always has been that as you go to finer and finer time slicing, that you can find some robustness. But basically the opposite happens, right? As you get to finer and finer time slicing, the fact that your order arrives 10 to the -4 seconds ahead of mine means that yours executes and mine doesn't. And so we have no robustness results as we go to this kind of finer and finer time slicing.
Yes, and even another thing that we also wish to explore is the fact that because all agents are learning and we can govern the pace at which agents learn, if the agents learn very fast, then every agent is going to constantly see a non-stationary environment and not able to reason about why certain actions had certain effects. So that is another point. So early on in multi-agent RL, when people were considering 2 agent systems, there were proposals on the learning rates being tied to each other in a particular ratio, which would ensure that the agents converge to a Nash equilibrium. But the moment we come to ABMs, we cannot enforce any such rule. So that is another thing that we plan to explore.
Yeah, I think, by the way, there's a paper by Blake LeBaron, which says that in a world where the learning rates can evolve, there's this kind of race to the fastest learning rate possible, and the agents with fastest learning rates can usually outperform those that have slower learning rates. But thank you for those comments.
That is a very interesting point, but there was also like a counterexample pointed out to me during my PhD where it's an example from Fudenberg and Levine, where an agent that is learning slowly knows that its opponent is learning fast. So it sort of plays suboptimally in order to force the opponent to converge to a suboptimal policy and then starts exploiting. So we do not know whether the learning algorithms themselves are strategy proof or no. And two current algorithms, RL algorithms, have sufficient capability to detect these sophisticated patterns.
And just as a footnote, let me mention that I think that in the finance world, those models have pretty much gone away from Nash equilibrium and subgame perfect equilibrium, for example, and it's much more just kind of an ecology of interacting adversaries.
Okay, that's good.
It reminds me, just in, this discussion reminds me a little bit of Rodney Brooks' subsumption architecture stories, right? Which actually my first ever published paper as an academic was one in which we placed a subsumption architecture into an agent-based model. We didn't have reinforcement learning. Reinforcement learning was in its nascency at that point, right? But it was an interesting little experiment that we developed there. Anyways, Tim, I see your hands up.
Hey, yeah. So okay, this is great. It's like two talks in one. One about agent architectures, which I think is really interesting and important work. It's stuff that's been kicking around the back of my head, but I don't have the technical powers to make any of that happen. It's very cool to see you doing it. But something I just want to make a link. We've done some work at RAND. We were actually able to get a hold of a whole city worth of mobile device ping data, which usually you can't get. And that's completely unscrambled, and they probably shouldn't have given it to us really, but they did. And we were able to do some fancy, Hadoop stuff on it to come up with an approximate contact network, both pre-distancing and post-distancing during COVID. And of course, it's not a small world network. It's not a power law network. It's certainly not a random network. It's kind of its own network, and it's got clumps, and it's got long links, and it's got all kinds of interesting properties. And of course, we've had to strip the heck out of it in order to make it shareable, but we do actually have an approximate topology of physical contact between people at the city scale. Now, we don't know anything much about those people. We know the block they live on, so we can infer some things, but we really don't know who's how old and that kind of thing. But if you have desire or interest in examining that, and we did some stuff where we found that vaccination strategy, vaccinating highly connected people, super effective because of the structure of the network. We haven't done as much of it as we'd like, and if you have use for it, please let me know.
Sure, definitely, because a lot of network related studies can be done here. Like since we don't know anything about the people, it might be tough to model disease spread directly. But we could ask the questions that if the page rank, high page rank nodes had these characteristics or had these interaction behavior, like what would be the consequence? And probably even look at things like scaling effects with different sizes of networks. Sure, that will be interesting. Ayush and I will try and get in touch with you and discuss like what we can do there.
Great.
Thanks.
Yeah, thank you.
Okay, well, we're right at our break time, so I think this is a good time to stop. And when we come back at noon, I believe Matt Kohler will be reconvening us. We'll have a couple of talks and then a framing discussion. So get your thinking caps on. We're going to break people up into rooms and kind of talk about a couple of topics related to IGSS. And then we'll have another short break before we switch to our keynote for the afternoon. So see you all in half an hour at noon Eastern Daylight.